All right, if you guys can take out the packet with all the pictures, that's going to be very helpful today. Packet with all the pictures. All right, section 15.7, we're going to learn what cylindrical coordinates are. Cylindrical coordinates, it'll feel very easy, okay? It's going to be very related to polar. So in 3D, we've been using rectangular coordinates, x, y, and z. And so what we're trying to do is we're going to introduce a new type of three-dimensional coordinate called a cylindrical coordinate, where now you're going to have r, like in polar, theta, like in polar, but the third coordinate will now be z. So, yeah? The third coordinate will be z. This z here is the same z as this one. Huh? Yes, it's not too crazy. It'll feel very similar to what you've been doing. Yeah. But the way you visualize how to plot a point is also a little familiar, but it's going to be a little different as well. Okay? So let's say there's some point floating in space right here, x, y, z. Okay? The way we're going to now graph this point is we're still going to use r and theta. Think of polar coordinates on the xy plane. Okay? At what axis does theta start at on the xy plane?
The positive x-axis.
Starts on the positive x-axis, right? And then it kind of goes like that. But now the positive x-axis is shooting towards us this way. So theta will still start here, and it'll rotate the way it was doing it on the xy plane, counterclockwise like this. Okay? So the way you're going to think about how to locate this point is this point has a z coordinate, but if I make that z coordinate 0, that z coordinate being 0 will now make this point on the xy plane. Right? So now that that point's on the xy plane, I use the same thing I learned in polar coordinates. I rotate by an angle theta on the xy plane, and I stretch by some distance r, like that. And then once you've located that point on the xy plane, you just move it according to the z value, either up if it's positive, or below the xy plane if it's negative. If z is negative. Everything you guys learned in polar will still apply. So for example, what's the relationship between a rectangular coordinates in xyz to a cylindrical? Well, you're still going to use the same exact same thing. R will still be r cosine theta. Y will still be r sine theta. X squared plus y squared is still r squared. But here, like I said, z is the same z coordinate. This z is the same as this z. So let me just have you do a little graphing, little point plotting. I would like you to plot these points that are now labeled in cylindrical coordinates: 2, pi over 4, 3, and we'll call this point B, -3, pi over 2, -1. Just to kind of get a sense of how you're graphing these points. Because I'm going to describe a lot of motion, like how these things move, but I would like you to try to do it on your own. So try to plot that in 3D space. These are in cylindrical coordinates, okay? Cylindrical coordinates. This is r, this is theta, this is z. This is r, this is theta, this is z. Starting this up here. Try plotting it. So if it helps, start on the XY plane first. The way you moved with polar with theta and r, same thing. Z just either levitates it or it brings it down. Let me walk around so I can see kind of how you guys are plotting this one. Where's your point? Oh, try drawing it. Try drawing it. I need you guys to practice drawing it because, you know, when you guys set up these integrals, everything's so visual. Everything's so visual. Yep. Correct. Yeah, remember when r is negative, it shoots in the opposite direction of the angle. Okay? Alright, let's take a look. Oops, I'm over here. Alright. This guy says we're gonna let's say this is 2 units right here. 1, 2. So r is 2 units. You're gonna rotate it pi over 4. Remember, this is 90 degrees right here. So pi over 4 is halfway. So it's gonna go something like this. Look. And then what do you do from there?
Like that?
You levitate it 3 units up. So let's see, 1, 2, 3. So A would be floating in space somewhere right here. Okay, so something like this. Like that. And then, let's see, how's that? So it helps it, again, if you just start on the XY plane, okay? 2 units out, rotate your angle, and then either levitate it or drop it down. All right, next one, we got pi over 2. That's gonna be on the y-axis. And now this guy's gonna shoot away from pi over 2, opposite. So if pi over 2 is over here, now it's gonna go 1, 2, 3 units in that direction, and then it's gonna drop down 1 unit. So it's gonna go like this. So B will be over here. Something like that. Oh, okay. Nothing too crazy, right? Hopefully, feels still very polarish. So if you guys look at your handouts, I gave you guys some visuals of some common surfaces we've been dealing with. So one of them is a cylinder. You guys look at the packet with pictures here. So in rectangular coordinates, if we have a cylinder that looks like this, x squared plus y squared is equal to 4, then you're going to use your conversion equations to turn it into cylindrical, meaning your equation can only have r, thetas, and z's. Okay? R, thetas, and z's. You can't have any more x's or y's. So what do we do with the left-hand side?
R squared.
This becomes r squared. So we get r squared is equal to 4. And just like you guys did with polar, square root both sides. You get plus or minus 2. But in polar, like I said, we usually just use the positive one. Okay? So here's how I need you guys to start visualizing these cylindrical coordinates. You guys see how this equation does not have any thetas or any z's? Okay, so this is z and theta are free variables. That means they can be whatever, they can vary. Okay, but r has to stay 2. So that means that this is 2 units away. You have this circle because r can rotate by any theta, but z could be anything that's positive or anything that's negative. So what do you guys think the graph of that would look like? Yeah, it's like if you had a little robot that had an arm that was drawing like a sketch, it would rotate all the way around, but then that robot can levitate while it still rotates, or it can go down, so it's going to give you that cylinder shape. It's a very different, it's the same surface that we've been studying, but the way you picture how it's drawn is very different. Okay? So it's a radius that just rotates, but it can also levitate or go down, so it's going to draw you this entire cylinder like that. And then you have the famous cones that we've been doing a lot in your homework. Usually the equation looks like this, the square root of x squared plus y squared. This is in rectangular. And then if you want to turn it cylindrical, do I have to do anything to the z? No, right? We can still use the same z coordinate here. But now the inside becomes r squared. And so we just end up with z is equal to r. It's cylindrical. So how the heck do I visualize what's going on this time with my graph? So let's take a theta. Let's just say you rotate by some theta, right? You stretch by some r value. Let's say theta is pi over 2. And you stretch r, let's say r equals 2. Okay? Let's say this is r right here. This distance r. How much do how much does z, what is the value of z now? 2. So then this is going to be 1, 2. So it's going to be that point right there. And see how you guys see how theta is free, the free variable? So that means that point will rotate like this, like that. But what if r is something smaller? What if r is like 1? Now what will z be?
1.
It'll be 1. And that point can rotate by any theta. So it'll be like this. So the smaller r gets, the smaller z gets. So those circles are really small circles to really big circles. So then they start becoming like this. Ah, shit. So that's how you end up with, that's how we're going to end up with a cone. Like that. All those circles that are getting bigger as r gets bigger. So yeah, so maybe let's write that. So whatever r is, z will be the same value, like that. All right. So I have another little practice problem for you guys. So convert into rectangular coordinates and sketch its graph. And so the equation is r squared plus z squared is equal to 4. All right, so convert. Right now it's in r's and thetas and z's, so it's in cylindrical. Convert it to rectangular. It should look super familiar. And then I want you guys to try to graph it. Hold on. I'm getting lightheaded. So now the mess is coming up. Get these visuals ready for you guys. That's right. All right, what did you guys get? What's the graph of this looking like? What does that become right there? X squared plus y squared equal plus z squared equals 4. Very familiar. What is that? It's a sphere, right? Sphere of what radius? Radius 2. Perfect. Yep, that's all it is. But now, now this is how you write the equation of a sphere, though, in cylindrical coordinates. That's what I want you to realize. Okay? All right. So, like, hopefully you're noticing cylindrical coordinates is basically just polar coordinates. Like x's and x's and y's are just polar coordinates. So that means that when we use cylindrical coordinates with our integral, when we convert a triple integral from rectangular to cylindrical, it's just polar for x's and y's. Because we're being polar in the spectrum. And so when we try to now bring this into triple integrals with cylindrical coordinates, since cylindrical coordinates just means x and y turn into polar coordinates. Into polar coordinates. Everything you learned in section 15.3, which is the one where we were talking about polar coordinates, carries through. And so what I mean by that is for a solid E of type 1, where you're bounding Z, where E is going to be bounded, you got your points X, sorry. Yeah. Where you have R, theta, and Z, but because it's type 1, you're going to bound Z. And let's say theta is bounded by alpha and beta. R is bounded by A and B. And Z is going to be bounded above by a function. Z will now be a function of R and theta instead of X and Y. Okay? These are the type of surfaces that we'll be looking at. So Z now will be bounded above by a function of X and Y. It'll be bounded by a function of R and theta. And it'll be bounded below by some other function of R and theta. And so when I want to compute this triple integral, that's originally in rectangular coordinates,
you're going to have z is bounded below by this function r g1 r theta, and bounded above by this other function g2 r theta.
Is that dv?
Say it again.
Is that dv? No, for the triple integration. So dv instead of.
Oh shit! Thank you. Do I have a here? Oh no, I did. Thank you. So z will be bounded below by this, and r is bounded from a to b, and theta is bounded from alpha to j. And oh, I hate writing this part, but your x's, y's, you're just gonna use the conversion that you guys did in Poland. Okay? So it'll be, instead of x, it'll be r cosine theta. Instead of y, it'll be r sine theta. And your z stays the same. If you're bounding, if I have the z here first, we're gonna have dz, right, first? But in polar, what happened when you converted to polar? What happened to the dx to y? It became what? R dr d theta, exactly. So because this is just going to end up using polar with x's and y's, what we learned in 15.3 is that this extra r gets popped out. So we have that additional r that you got to make sure you don't forget. So don't forget this guy. It's still going to carry through because we're basically making x and y polar. And so it'll feel very similar for cylindricals.
Do you necessarily always want the r integral to be the middle integral?
It ends up happening so because usually, as you guys, if you're noticed on the problems in 15.3, r sometimes is bounded by a function. And theta will always be bounded by a constant, which is why theta usually tends to be outside. Cool. So it's pretty much 15.3, but now we just have the triple integral part to take into account. Okay. So let me show you a problem that'll look similar to the homework. Then I'm going to have you guys try one out. I picked one these problems are a little more complicated than the ones we've been doing, okay? Because the homework is getting more complicated. Okay, so I want to make sure we practice some more challenging problems here. All right, so this guy says this. It says evaluate the triple integral where E is the solid, make sure I read this correctly, is the solid that lies within the cylinder, x squared plus y squared is equal to 1. It's going to be below z equal 2 and above the cone z equals the square root of 4x squared plus 4y squared. Throw a 4 in there. Make it a little bit nastier. And this is the triple integral that we're being asked to do. Yeah. Okay. Okay. So if you're not doing this on your homework, you have to sketch something. Because now there's all these surfaces playing with one another and it's getting a little gnarly here. Okay, let's see if we can maybe try something out. Let's see. X, Y, Z. Okay. So let's go step by step. Let's draw some of this stuff here. Let me let's try to convert some of this stuff into cylindrical coordinates. Okay? You guys want to try to sketch first or do the algebra first? What do you guys normally do? You do a sketch first? Okay, let's do the sketch first. All right, we have a cylinder, x squared plus y squared is equal to 1. So it's a circle of radius 1 on the xy plane, and then the cylinder will shoot up. So we got that kind of shape like that. What does that look like? Z equals 2. Big flat plane. Let's say it's 1, 2. Let's say it's right there. So then that's just this plane kind of shooting like this. So it's going to intersect. Right here. Cool. And then we have a cone going up. So here's where this can get tricky. Is the cone, like we don't know how wide the cone can be, right? If the cone is coming here, then it seems to kind of be a little funky where it's going to be, remember, if the cone's facing up, what does it mean to be above the cone? It means to be inside the cone, right? So if the cone's like this, then we have this like kind of weird solid that looks like that, right? So we have to figure out the slant of the cone a bit in this case. Okay. I want you guys to notice I can factor this like this. Okay. So if I want to figure out where the cone intersects the cylinder, how can we figure that out?
With R equals.
You get through from C equal to R and R.
Yeah, this is the cylinder equation, right? This is the cone equation. But when they intersect, what must be true about x squared plus y squared? So let's write this, intersection of cone and cylinder. Let me organize it a little bit. So here's the cylinder. We have x squared plus y squared is equal to 1. And then the cone, I'm rewriting it on purpose like this. Right? So when they intersect, what must be true about x squared plus y squared on the cone? It's going to have to be equal to 1. Yeah. Because on the cylinder, x squared plus y squared has to equal 1. So then if I plug that in here, I get z equals the square root of 4 times 1, which is the square root of 4. So it gives me plus or minus 2. So where is the cone intersecting the cylinder? At what z value? At z equals 2. Exactly where the plane is intersecting the cylinder. You see that? So that means that the cone is actually perfectly intersecting it right there. And boom, right there, where z is equal to 2. That's what this shows here. So then, if I'm going to be within the cylinder, so I have to be inside of the cylinder. Within the cylinder means inside of the cylinder. Below the plane z equals 2, but inside the cone, what is that shape going to end up looking like? It's just the cone itself, right? Or like the inside part. So it's going to be the cone got a haircut. Yep. It's going to be this part. That's solid. Yeah, come on. Yeah, take it. The function, you're told the function. Yeah, you're told the function. This is the function f of x, y, z. Yeah. Yep, go for it.
So, is there an actual difference between if you write over R or the integrals over D or the integrals over D? Or is it, are they interchangeable?
Oh, the letter?
Yeah.
Normally, the letter E is used in this book for a solid, and D is used for a two-dimensional region. Yeah.
And R is just a general reading.
And R is usually a rectangle. Yeah. And then I think we use B for a box. Okay, so this is the solid now, right? All right, we're gonna try to bound it. So here's what you guys have to try to do, what we practice on Thursday. Is it a type 1 solid where I bound Z? Is it a type 2 solid where I bound X? Or is it a type 3 solid where I bound Y? Okay. Hint, we're doing a section on cylindrical coordinates where usually we're hoping it's a type 1 solid. Exactly. The other hint, exactly, is that you're having a lot of equations with Z isolated already. So that usually means try to do bound Z instead. So if we bound Z, whenever we're poking this guy, going up towards the Z axis, like that. So if I poke it, notice that it's going to start here, and then it's going to end up at the plane of this. Yeah. So what's bounding it below? The cone, right? So yeah. Okay, this is the algebra part that I was going to say. Okay. Let's say we have the cone equation, which is Z equals 4 times x squared plus y squared. Let's turn that into cylindrical. That's going to be what in cylindrical? 4r squared, which is going to be 2r in cylindrical. We're going to use the positive square root. Okay? So in cylindrical, the cone is Z equals 2r. Okay? The cylinder, which is x squared plus y squared, becomes, in cylindrical, that's going to become what? R squared equals 1, so it's just going to become r equals 1. Okay? Another reason this is called cylindrical coordinates is because cylinders have the most basic equation, r equal a number. That will be a cylinder in 3D. Yeah, and the plane is just Z equals what? Z equals 2, right? So it's bounded below by the cone and bounded above by the plane Z equals 2. Is that cool? Okay. So then that means when we start doing our, we're going to put all this together now. And so we have a type 1 solid. And so when I start computing this triple integral, let's start doing our bounds. So we have Z, you guys said, is bounded below by the cone, 2r, bounded above by the plane, 2. And so I'm trying to do this in cylindrical coordinates. What does x squared in cylindrical become? It's just r, yeah, it's r cosine, but you're squaring that, so it becomes r squared cosine squared, right? Let me go, yeah, I'm turning to cylindrical, so what happens to the dv? That r pops out. That r pops out. And I'm bounding z. Okay. I need to do the r's and the thetas now. So since I bounded by z first, what do we do to the solid? It's going to be projected onto the to the XY plane. So notice if you project it to the XY plane, what do you guys see the shape's gonna be? Circle, the circle of the actual cylinder, right? So it's just gonna be the circle of that cylinder. When I graph that as a circle of radius 1. And so if I try to do this in polar, what is R bounded by? Yep, it goes from 0 all the way out towards 1. This is going to be your R. And your theta? Todo, the whole thing. 0 to 2 pi. 0 to 2 pi. So it'll feel very like triple integral when you're doing the z part, but once you get to the xy plane, it feels very 15.3. dr second, and then d theta is last. Let's see, clean this guy up a little bit. Theta goes from 0 to 2 pi. R goes from 0 to 2. Z goes from 2R to 2. And then I think it's just the R, right, that gets multiplied in there? Do I distribute it like this? Or is it just literally multiplied with R? Yeah, it's just multiplied by R. So it's R cubed cosine squared theta dz dr d theta. But you're integrating with respect to z. So this whole ass thing is just a big constant. Take it out. Is it cool if I leave the rest for the notes? You guys want to keep going? I'll keep going. It's okay. I'll keep going a little bit. Let me keep going. Let me do a couple more steps. Let's do a couple more steps. Okay. So I got theta, 2 pi, R, 0, R, 2. Okay, now we're going to integrate this with respect to z. This is a constant, so it's a constant times z. Where z goes from 2R to 2. Okay. And then remember from here, now we just plug in the bounds. So we're going to plug in the 2 here, and then minus the 2R here. Okay. And so you end up with, this will be the last step. 2 pi. R goes from 0 to 2. All right, let's see. You plug in the 2 here. Oh shit, did I change the R? Look at that. Jesus. Thank you. 1, 1, 1. Sorry about that. I think this 2 threw me off. Okay, let's see. This will give you, with the R here, you're going to get 2R cubed. There's cosine. And then when you plug in the 2R here, you're going to get minus 2R to the 4th. Is that okay right there? Plug in the 2 in for Z, put that in front, you're going to get a 2R cubed. Okay? You can. Yeah. This is times cosine squared theta. Okay? So yes, so if you keep going, this is going to look like this. It's going to go cosine squared theta times 2R cubed minus 2R to the 4th dr d theta. Okay?
These bounds are just scalars. So what is the nice property that we learned? Integrate them separately, yep, and then multiply the product. So then this will just become theta goes from 0 to 2 pi of cosine squared theta d theta times r goes from 0 to 1 of 2r cubed minus 2r to the third. Okay. I've helped several people this past week. Some of you guys are forgetting about what to do here with integrating an even power trig function. There's no use of nothing fancy here. What you end up having to use is an identity. Cosine squared equals 1/2 1 plus cosine 2 theta. You have to make that conversion with trig identities. And then you'll be able to replace that with that, and then that you'll be able to integrate. Okay? Yeah, don't forget that. There's this guy here, and then there's the sine squared one, which is 1 minus cosine 2 theta. Make sure you put those in your index card, so you don't get, if that shows up, you don't get stumped. Yes?
Are you okay if we use the reduction formulas, if we know them?
What's the reduction formula? Remind me what that is?
It reduces the power by 2.
Okay. Let me look it over. I think it should
They're
be.
in the back of the canvas, but
Okay.
our 2 teachers are very adamant about no reduction formulas
Okay.
whatsoever.
I have to see what they are. I don't think I remember what they are.
It looks like the question by parts.
That is useful more than the power is like
If the power is to the 4th power, if the power is to the 8th power, maybe not. I won't do that to you. If the power is, let's say, to the 4th power, then rewrite it like this. Like that. If it's to the 4th power. If it's any even power, you just put a cosine squared in here to the power of whatever you need here so that it gives you that even power. So if it was like to the 6th power, you write it as cosine squared to the 3rd. Okay? And then this, you still would replace it with that. It gets nasty though, because then you have to FOIL it out. Yep. Hopefully that's coming back a little bit. Talk to. Okay. If it's an odd power, let me just finish this one. If it's an odd power, like let's say cosine of 3 theta, then you split it so that you get an even power and then an odd power like that. And then here, you want to use a different identity, which was the Pythagorean identity. So that you can write this as 1 minus sine squared theta cosine theta. Okay? Why do I want to do that? Because now that I have sine and cosine, I can do u substitution. You let u equal sine theta, du will equal cosine theta d theta. You'll be able to use the cosine theta for the du part, and now you can rewrite this as 1 minus u squared. So it's a completely different strategy when you have an odd power trig function. Okay? Even you use this bad boy, like that. Odd power, you split it, and then you just leave one of the powers alone, and then the other powers will be even. So you'll be able to do u substitution that way. Okay, sorry. This ends up, you finish this out just to kind of, in case you try to do it on your own, this ends up equaling 3 pi over 5. Okay? Does that 3 pi over 5 equal the volume of this cone? I swear I should put that as a test question somewhere. It does not. Because remember, you're doing hypervolume.
you're finding some funky hypervolume between this function, which is a three-dimensional function, and that solid. It's like this weird volume between those, the solid and the graph of that fourth dimensional thing. But yes, it does not equal the volume of the solid. Don't forget. Yeah, Jacob.
Yes, it always measures some volume that's one dimension higher than
It always gives you some volume that's the integral will always give you a volume that's one dimension higher than what you're integrating over. What you're integrating over. So a single, you guys did a single integral, right? This was just an interval from A to B. That was a one-dimensional thing, but the integral gave you area, which is a two-dimensional. All right, let's see. So here's my practice problem for you guys. You don't have to finish the integration. Just do the setup. Try this out. I'll go around, help you guys out. So set up the triple integral in cylindrical coordinates. Where E is the solid between the cylinders. X squared plus y squared is equal to 1, and x squared plus y squared is equal to 16, is above z equals 0, and below z equals y plus 4. So just set it up. On the notes, I actually do the whole integral though, in case you're curious how it works out. Say it again?
it will also be an x
It's between these two cylinders.
also just
Oh, shit. Hello. Thank you. And this is the function that you're integrating, x minus y. Sorry, thank you. You can try to do a short sketch. If you're trying to figure out what maybe this looks like, quick things to just remember this class. If you have a linear equation, meaning all powers are to the power of 1, it has to be a plane. Okay? If you're trying to figure out the slant of this plane, try to picture what it would look like if you just graphed it on the the YZ plane. If you were to graph this equation on the YZ plane. Bless you. All right, guys, do a quick check-in. If you already finished setting it up, maybe help out your classmate, give him some pointers. Do a quick check-in, guys. Go for it.
If I pencil there's a bigger cylinder, and my plane right here, it's more than 14. This area between the cylinders, but under this plane, which I didn't really draw the plane, that should be more square. And then above this, it's like that big piece between the donut.
I'd probably end up the same thing.
Oh, I see it. I did that, but
I did it other better.
That was really good.
It takes me like a long time to draw the pictures. Like I have to use a ruler, like mark everything.
That's good. I realize that the high school what equation is it? Oh, yeah. Oh. You could do that, but it's not anymore. I'll tell you what you don't want to do. You could do it. It's just, now you're down in par. Oh, what's the biggest part of that? That will take care of that part, getting rid of that part. Oh, the data is 0 to 5. Thank you. Yep. Just put it.
Oh, yeah, it's like, oh, I forgot.
Okay.
I see.
All right, guys, you should have like a toilet paper roll that was sliced, something like that. If you wanted to sketch it, okay? How do we know the slant of the plane? Keep in mind, if I was to graph this on the YZ plane, it has y-intercept 4 and slope 1/1. So the line would go like this. If I was to just think of this as a linear equation in 2 dimensions on the YZ plane, so that kind of gave me my slant of my plane. Okay? Don't worry too much about the slant though. Notice that Z is going to be bounded below by the XY plane, which is down here, all the way up to that slanted plane, right? So you're going to have your Z. What did you guys put for the bound below? Bounded below by z equals 0, and bounded above by the plane, but you're writing it in cylindrical, right? So it's going to be r sine theta is 4. Convert these to cylindrical. R cosine theta minus r sine theta. What does this make happen though? That extra r comes out. Okay. Now let's see what r is going to do down with that. Notice inside there's this circle, so you're not using the inside part of the circle, right? So your r is going to stretch. What's the radius of the big circle? Radius is, what's the radius?
4.
4. You guys are you need the Halloween candy, man. The smaller radius of the smaller circle, what is it? 1. Okay? So notice that your r is going to stretch from 1 to 4. Okay? So r will stretch from 1 to 4, and then your theta, the circle goes all the way around. So theta is bounded by 0 to 2 pi. I'm just having you set it up so then you would stop it. On the notes though, I solved it, but it's fucking kind of a doozy. Okay? It's a doozy because when you bring this guy in, the algebra gets worse. Oh, I did forget the DR.
Minus 2 points.
Minus 2 points. Yeah. So you guys see how it feels kind of still 15.3-ish? It's just this new part. Yes. No.
For the drawing, would the plane like touch the edge of the bottom circle?
Oh, does it? Let's see. Yes, it does. It does. It does because it's over here. That's going to be at -4, right? And when y is -4, z should be 0. You're right. Actually, it should be like hella slanted. Now, I will give you no points off though. It's just a sketch for you to understand that this is above, this is below, and you don't include the inside. That's what I would be grading. That's cylindrical coordinates. It's basically just polar. Okay? I want to spend more time on 15.8. That is brand new. You've never seen this before. So that we'll spend more time on. Very visual, right? These triple integrals. Okay? But it sounds like you guys are getting some of the hints, right? So I see equations where z is by itself, so I'm going to probably start bounding by z. Okay, let's go on a break. 2 o'clock. Go get some Halloween candy.
Wait, is there a spot with Halloween candy?
It's kind of far. It's the Math and Engineering Student Center.
I thought you were going to say the store.
Come back at 2:10. No. Say your homework. You know what set this is? Is it 17? You guys show your character.
台灣老師又唔俾我問，之前我去問就話我唔會，台灣老師都攞，正我
For today? Oh, 17.
啊，即係我好似參加之前問嗰啲 lecture 咧，佢話我唔會，然後我唔想問，相當難啦咁，你問咯，咁我嘅唔識先嚟啦。
All right, bring it back, guys. Bring it back. All right, so we're gonna do something brand new that you guys have never seen. Something called spherical coordinates. And this time it's gonna use 2 different kinds of angles. So that's where this new thing comes in. The r and the theta are still similar. They're still kind of from polar, okay? But this is how you're gonna want to think of first, let me write this down. This is a picture that you have in your packet. Okay, you have this picture in your packet. And we have rectangular coordinates, and then what we're going to call spherical coordinates. Again, rectangular is x, y, z. This is something new here. So we're going to call guys, you have your point here, right? You have your point 3D space. The distance that this point is from the origin is going to use a new symbol called rho. Okay? So it represents that distance from the origin to that point. That's rho. You're still going to have theta, which is the same theta from cylindrical coordinates, that starts in the positive x-axis and then rotates this way. It rotates so that, again, if you were to project this point onto the xy plane, that's where theta is going to rotate. So that's still it's similar to cylindrical. But now you're going to have a new angle called phi. So this is RHO, and this is phi, PHI. Sometimes people call it phi. Phi, phi, phi. I call it phi. Okay? Doesn't matter. That's Spanish, probably. All right. Let me show you the motion of this guy here. Perfect to have a ruler. Okay. So go ahead and stand up. Come here, stand up. And then just put your finger up your arm, your fist out like that. So, yeah, like that. It's perfect. Okay. So just go in there. So his fist is a point. Okay. So instead of going x, y, z, right? It's going to go like this. It's going to go, you can project that point onto the xy plane. So I'm a little machine. I'm going to rotate theta so that it's right below the point. Okay? Now I have this new angle that's going to start at the positive z-axis called rho. Sorry, it's called phi, And then that phi, starting from the origin up to the z-axis, rotates downwards like this. So that when it rotates downwards, it's pointing towards the corner. That's what this motion is doing. And then rho, kind of like R, rho starts from the origin and then it rotates, it stretches all the way till it reaches the point. That's the motion that's happening.
So,
Okay.
so rho is the like the magnitude of the position vector.
You can think of it, yeah, like if I was to draw a vector from here to here, rho is like its magnitude. Okay. Yeah. Okay. But that's kind of the motion that's happening. But there's a whole bunch of other little details. Okay. Unlike R, rho is always going to be. It's never going to be negative. Okay. So rho will always be going to be greater than 0. Rho will always be greater than 0. Theta is still the same good old theta from 0 to 2 pi. It rotates one full circle only. But rho, god dang it, I keep saying rho. Phi can only rotate from the positive z-axis towards the negative z-axis. How much angle rotation is that? Only pi. So phi can only go from 0 to pi. Okay? Yeah.
Is it like parallel to the ZY plane, or is it any spin?
Is what? Is say it again.
Phi, when it can only go from 0 to pi, is that any rotation?
Yeah. So like let's say this is the origin. That's positive x, positive y, like that. If I want to go behind me, theta takes me there. and then rho, and then phi just goes. If phi is between 0 and 90 degrees, you're gonna have to be above the xy plane. But when phi now goes below 90 degrees, between pi and pi over 2, now it's gonna be below the xy plane. So theta is what helps me move to different octants. All right. So because this still is using theta and r, we're still gonna use what we learned in cylindrical to help me find conversions in spherical. Okay. So from polar or from cylindrical coordinates, we still have x is r cosine theta, r sine theta, but do you guys see this right triangle right here shooting towards you? Okay. Let me draw it right here. Here's R, here's Z, here's rho. Do you guys see how this line segment is parallel to the Z-axis? Little fact of geometry. Since this rho is phi, this is congruent to this angle because these are parallel lines. Fact from geometry. You have two parallel lines and you cross them through another line. The opposite angles here are going to be congruent. So this angle is also phi. Okay. Therefore, this is angle phi. So the relationship that R and rho have, since this is a right triangle here, is notice that if I use sine of phi, that's going to be R over rho. Multiply both sides by rho, and we get that R equals rho sine of phi. Okay? We put this together, and then we say, okay, well, since R is rho sine phi, and X is R cosine theta, let's replace the R with rho sine phi. So then that gives me my conversion. X is going to be rho sine phi cosine theta. Y equals rho sine phi sine theta. So that tells me how to convert between spherical and rectangular with x's and y's.
So the theta is the same as the cylindrical.
Yep, the theta, the r are the same. This triangle, I can also use cosine. Cosine, what's cosine of phi, guys? Phi's right here, right? Adjacent over rho. Multiply both sides by rho. So then I get z is just rho cosine of phi. Okay. What does that mean? That means that when I want to change from rectangular to spherical, all the x's are going to be replaced by this expression, all the y's are replaced by that, and all the z's are replaced by this. Hell, more complicated. Okay? So these are your conversion equations. These are the conversion equations between rectangular and spherical. All right, let's write some more comments here. This guy, let me just write what I said, is the distance between the point and the origin, which is why it's going to be positive. Can you see that, Sam? Theta, again, still starts at the positive x-axis. And then this guy, this new angle phi, don't forget that it starts at the positive z-axis. Starts at the positive z-axis. Let me see. Let me see if I have something on GeoGebra already built. Oh, I do. Sweet. Okay. Okay, look at that. Okay, that's it. So let's see what a sphere is going to look like in spherical coordinates. The equation of a sphere. Let's fill up oh, I forgot one more. I apologize for the pen writers. I forgot for the pen writers. Since rho is the distance between this point and the origin, how would you find, if I use the distance formula, right? Rho would equal the square root of this x coordinate minus this x coordinate, right? This y coordinate minus the y coordinate of the origin, because it's just using the distance formula. So the other conversion equation is rho squared is x squared plus y squared plus z squared. I forgot that one. Conversion equations. Sorry. So anywhere I see x squared plus y squared plus z squared, I can now substitute it with rho squared. Okay? So when I have a sphere, give me a random radius, guys. 2? Okay. Spherical. All right, so let's say I have a sphere of radius 2. That's what it looks like in rectangular coordinates. But when I turn it to spherical coordinates, what does the left-hand side become? This becomes rho squared. Equals 4. Square root both sides, you get plus or minus, but rho has to be positive 2. Okay? And so let me show you kind of what's happening here. You got 1, 2, let's say. Your rho stretches 2 units. The angles can vary. I can vary my angle this way for theta, and I can vary my angle this way for phi. So let me show you guys before I draw it. Let me show you guys this helpful visual here. Oh shit. Hey, there you go. Okay, so let me, so notice, let's go down. Okay, so here I got my sphere. Okay. Let me make all these, zero. Okay. I rotate theta, right? Uh-oh. Shit, hold on. Oh, let's say phi is pi over 2. Let's say it's like right here, pi over 2. Let me go halfway. Okay. What's happening is rho right now, rho is 1 unit. Notice that it's 1 unit away, right? but I'm allowing theta to go from, let's say it's 2 pi. Theta can rotate from 0 to 2 pi, and phi can rotate from 0 to 2 pi as well. So all the possible points, rho has to be 1 unit, right? It can stretch 1 unit out, but theta can only go from 0 to pi, and phi can only go from 0 to 2 pi, and phi can only go from 0 to 2 pi as well. So if I do that, if I just let that vary, it's only going to give you this part of the sphere. From where theta goes from 0 to pi over 2, and phi goes from 0 to pi over 2. If I let phi go from 0 all the way to pi, now it'll be able to vary all the way down towards the negative z-axis. But theta can still only go from 0 to pi over 2. I can then say, well, I want more of my sphere, so let's have theta hold on. It's not. All right, give me 1 second. Technical difficulties. Hold on. Let me sign in. You had a question though, Sam. I answered. Okay. All right, hold on. This is 15.7. Spherical. Here we go. Let me reload it. Hold on. There we go. Okay. So we had phi goes all the way to pi, and then now I can rotate my theta at some larger angle, and notice that it's missing a piece of the sphere because theta can only go from 0 to whatever this theta angle is here. Okay? It's just the surface because rho right now is only going up towards 1. If I make rho 2, it'll just make a bigger sphere. But it's still just the surface of the sphere. Okay? So if I change my phi, I'm only allowing that phi to rotate to whatever that angle is that I stopped it at. Right here. Okay? And then if I make my theta smaller, then it removes it so that it only goes from 0 to whatever that theta is. Okay? All right, let's see. So here I don't have any bounds for theta and phi. So theta and phi are free. That means that as long as my rho stretches out 2 units, I can rotate this all around theta, and I can rotate all around phi. So it's going to give me the entire sphere. Just the surface stuff. Okay? There are no restrictions for theta or phi like I showed you on the computer, so it gives me the entire surface. So this is the spherical equation of this guy is literally just rho equals 2. Which is a lot nicer when you're starting to bound things, right? Than a polynomial, a quadratic polynomial. This is just a really easy linear equation. Let me show you one more. And I'm gonna have you guys play with it. Let me show you a cone. But this one's facing downwards. So in rectangular coordinates versus spherical coordinates. So if I want a cone to face downwards, now I'm going to do the negative square root of that. So what you will need to do is
I want to, eventually we're going to bound all this in spherical coordinates. I want to write all this in spherical coordinates. So all the x's, y's, and z's have to be gone. I have to have rhos, thetas, and phis. Check it.
This is a question about this basically find elements by this.
Yep. Yep. That's what's going to make it hella easier. Yeah, so this is called spherical coordinates because equations of spheres are super basic. This is rho equaling a moment. Correct, yeah. We'll get there. We'll get there with the triple number. Yeah. Right now I'm just having you guys get used to spherical coordinates and learning how to convert. So if I want to convert this to spherical coordinates, what do I have to change the z into? Rho cosine phi. Okay? So the z becomes rho cosine phi. And then here's a little tip for me. I can write x squared by squaring all this. And I can write y squared by squaring all that. The algebra will still work, okay? But instead, what you're going to want to do is you can also bring this guy along. Oh, shit. No, yeah. You can still bring this guy along. Because what is x squared plus y squared in polar? It's really just r squared, right? So this is really just r squared. And by doing that, I've converted this to an r squared. What happens when I square root the r? You're just going to get plus or minus, but you're going to want to have it be negative r because of the negative here. But what is r? It's spherical. Cosine phi. So then that means I can now write this as cosine phi and minus rho sine phi. So it's kind of like you can go from rectangular to cylindrical and then hop to spherical using this little fact here. It makes the algebra hell easier. Okay. Okay. See how they both have a rho? We can simplify. Divide both sides by rho. So you get cosine phi is equal to negative sine phi. We can simplify some more. What do you guys want to divide by here?
Sine.
Cosine or sine?
Sine.
I'll say sine. You could do cosine as well. Okay. Now, what does this become? That becomes cotangent of phi equals -1. Do the reciprocal. That's the same thing as if you just got that as well. Right, the reciprocal of cotangent is tangent. The reciprocal of -1 is -1. Is that cool? So some of you guys aren't convinced. You're like, no, I'm not convinced, punk. Cotangent, remember, is 1 over tangent phi, and -1 is -1 over positive. So flip these, and then you just get that. Let's keep going. What angle, so that phi is in between 0 and pi, see that's where this comes up now, has it so that tangent is -1. Is it pi over 4? 3 pi over 4. 3 pi over 4. So this tells you that this has to equal 3 pi over 4. Okay?
So we kind of take all students take calculus and we just shift it to our perspective.
The third quadrant, yeah, in this case. Yeah, because you need tangent to be -1. So let's see, why the heck is that supposed to be a cone downwards though? Let me do it right here. Let's see why it's a cone downwards. Which variables are free?
We got rho is free. Rho and theta are free variables. That means it could be whatever you want them to be, but phi has to stay 3 pi over 4. So phi starts here, rotates pi over 2, but then it rotates 45 degrees more, so now it rotates down to here. So this is 3 pi over 4 phi. But rho can stretch it, whatever I want. Rho can stretch as far as it wants, and because theta is also free, it can rotate all at once. So that's going to make this piece of this line segment that stretches also rotate like that. So it's going to make this cone right here. Yeah. That angle, no matter where I rotate phi, however I rotate it to my cone, it'll always rotate 3 pi over 4 radians down. Okay? If this was positive, this is 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 positive. So what would phi be if it was positive? Be pi over 4. So then that means it would have only rotated 45 degrees. So it would have given you the cone that goes upwards. Okay. Cool. Okay, let me have you guys practice, do a little bit of spherical coordinates here. So let me have you do 2 things. One, plot the spherical coordinates like I had you do for the cylindrical ones. So plot point A, which is 2 pi over 2, 3 pi over 4. And then plot point B, 3 pi over 2, pi over 6. And then I want you to convert into rectangular coordinates. Rho equals 2 cosine B. Oh, and plot and graph. Number 2, you have to do a little algebra, okay? Yeah, so plot these points here. So you start practicing the theta, the phi, and then the rho.
So theta is only on the XY plane?
The theta, yeah, it lives on the XY plane. Yep, exactly right. It's still the same one from polar coordinates. But it doesn't go more than 100 degrees. Yep. It's a half circle. Correct. Yep.
recording you guys?
So here, I'll give you guys. Start with theta, the more familiar one, okay? 90 degrees. So you know that you're going to rotate. It has to be somewhere on this axis, okay? That's that guy. But then your phi rotates 3 pi over 4. So it's 45, another 45, and then another 45. Kind of like this, right? So then, but when you're rotating your phi, right? Your theta makes it so that your phi rotates down this way, not like somewhere else. So theta is 90 degrees. Phi then says go 45, 45, and then another 45. So then that will make you go 45, 45, another 45. And then stretch it 2 units. So 1, 2. But like literally below the y-axis. Okay? Yeah, start with theta. Start with one of the angles. Yeah. I could have started with phi. 45, 45, 45, and then theta was put in right back. Let's just do number 1 together. I think a lot of you guys are struggling with it. So this is 90 degrees, right? That's the one that we plotted A. So your theta rotates 90 degrees towards the y-axis, but then phi makes it go 45 degrees below the xy plane. And then you just stretch your row 2 units. This guy here, this is your theta. It's going to rotate 90 degrees, another 90 degrees, and then another 90 degrees back here. So it's the negative y-axis. But then your phi only rotates, how many degrees is that? 30 degrees. So when you bring down your phi, it's only going to go down 30 degrees, but towards the negative y-axis, because that's where theta put you. So it's going to go like this here, but then phi only goes down 30 degrees here. And then you stretch it 3 units right here. So in this direction here. 1, 2, 3. So it's right above the y-axis, 30 degrees this way. I agree, it's a little challenging. Okay. All right, unfortunately, we're going to move on. So let's finish this part up because we have 30 minutes. Anybody that was able to figure out how to start this out?
So I said it's rho equals Z divided by the
Rho.
I mean, yeah, rho equals 2Z.
2. Rho equals, say it again. Okay.
Rho equals 2Z.
Oh, I see what you're saying. Okay. Okay. I see what you're saying. No, you did it. So since Z equals rho cosine phi, you're saying if I divide this Z here,
No. Divide by row, is that what you're doing?
Yeah.
So that's just, okay, so you're replacing the cosine phi. You're replacing the cosine phi with z over rho. Gotcha, okay?
And I did rho squared equals to 2z.
Okay, so you multiply both sides by rho, it looks like?
Yeah.
Huh?
And I did x squared equals y squared equals z squared equals 2z.
Equals to 2z, okay?
And nothing more.
And then you're done from there? Okay, so,
Oh wait, I realized something. You can like wait, can you completely square?
at some point, Sam, is that what you're gonna say? Yeah. So yeah, what would you do to start doing that though? Subtract both sides by 2z.
And add 1 to both sides.
Yeah, so when you're gonna complete the square, basically, you're gonna add something here, right?
Shift x squared plus y squared as 1, and then just do.
Yeah, exactly. You're gonna complete the square of this guy. Yeah, so you're gonna add both 1 to both sides, so you complete the square. So then that way that will factor into x squared plus y squared plus z minus 1 squared is equal to 1. Okay. So what do you guys think that is? The graph of what?
Sphere.
Sphere, but where's the center of the sphere?
0, 1.
It shifted up 1, correct. So it's gonna look like this. So the center was shifted up here and the radius is 1. So it's gonna be the sphere of that. That is way more complicated looking than just that. Okay. Yes, yeah, Jacob.
The graphic R2 cosine theta both limits is really a circle of the.
Yeah, exactly. Yeah, so his comment was when we were doing polar and you guys were doing that graph, it was a circle that was shifted like 1 over, kind of the way the sphere got shifted 1 up. Just a little. And I think he's noticing the similarity of the equations. Nice, yeah. Okay, guys, so we haven't even done integrals yet. Let's see how this is going to tie in. There's a picture. I'm not going to spend too much time. I just want to show you guys kind of like the reasoning. Oh, yay. Bro, I'm getting so many technical difficulties today. It's so annoying. Hold on. My notes don't want to load. Fuck you, dude. Okay. May I drop it? That's right, punk. Figured it out. Okay. So let me just show you guys. I'm just gonna kind of walk you through the reasoning of this following part, since you're not going to be expected to do it. Okay. This will be in the notes, but I'm not gonna. You're not expected to like compute this. I just want you guys to see what's going to happen. Actually, I'll leave this. Okay. When we want to do integration, I'm not going to have you guys do that, okay? But when you're going to do integration, you're going to have a spherical cube. How would you have, a polar rectangle?
we're gonna have like a spherical cube where your rho will be some rho for this arc here, and then a larger rho for this other arc here. Your theta will stay the same theta within this interval here, where this is the thetas here, the change in the thetas. And then this is the change in your feeds. That's when you throw the feed. So if we want to compute the volume of this small spherical cube, we would want to do this length times this width times this height. Okay? Because of the fact that it's like circular, these are arcs of circles, or like circular arcs. So let me say that way, circular arcs. So either from pre-calculus or from geometry, it says recall that there's a length, that to find the length of an arc of a circle, what you do is you multiply the radius of the circle times the radian measure between the arc. Okay? So how many radians did it change? Yeah. That's kind of like this radian change. How many radians is this changing by? Okay. So the length of this arc times the length of this segment here times the length of this arc. That's how we're going to find the volume. So delta rho gives you this length here. That's the change in rho. This guy here is giving you the length of this arc. So there's a circle of radius rho I, and then the change in your delta phi. That's the arc length right here. And then this arc length, it's a little bit more complicated. Okay. This arc length here uses this fact down here that this is the change in theta, but the radius of this arc is Ri. It's your Ri, your polar arc. Okay. So we have this arc length, which is representing this one. Okay. We have this arc length, which is this arc length here, and then you have your delta rho, which is your change in rho. Multiply those three things together. But because we're turning everything into spherical coordinates, the Ri gets changed in terms of rho sine phi. Okay. Well, this is an I and K, but it's like the increments of all your segments of phi and segments of rho. Okay. So what's going to end up happening, the summary is, when we're going to do a triple integral, your delta V is going to become delta rho, delta phi, delta theta. But remember when we switched to polar, there was an extra R that popped out? When you switch to spherical coordinates, what gets popped out is a rho squared sine phi. The reasoning is this part here. I know. Okay. So this tells us that the volume of each spherical rectangle changes by a factor of this bad boy here. So that's what's going to be the extra factor that pops out. That when we change it to spherical coordinates. Again, I'm not going to expect you guys to like do this on the test or anything, but I just need you guys to remember what you're going to have to do when you switch to spherical coordinates. That part I do want you to remember. So converting a triple integral into spherical coordinates. Spherical coordinates. So for a function in 3 coordinates, when converting into spherical, over a solid E, where let's say when you convert to spherical, you have that rho is between A and B. Theta is in between alpha and beta. And then phi will be between C and D. Then we're going to get that your spherical, your triple integral here. If these are the things that are bounding your solid, I wrote phi twice, I did write phi twice. Sorry about that. Thank you. Yeah, theta should be between alpha and beta. These are going to be your bounds in spherical coordinates. Usually, you start with rho first. But the beauty is that everything will be a constant. Okay? Theta goes in between, usually. If they're all constants, it doesn't really matter, but usually you have theta in between. And then we have phi at the end. Your x, your y, your z, all those have to turn to spherical. So I apologize for all the writing. So it's going to be rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. But as I was showing you with the diagram, the volume ends up getting scaled by a factor of rho squared sine phi that pops out. So then you get d rho, d theta, d phi. Yeah, so this is the new r that gets popped out in spherical coordinates. That's going to be the new r that gets popped out. Cool. So yes, it's going to be kind of a lot of work to do your setup, but once you do, it'll be totally worth it because all the bounds are going to be nice scaled. Yeah, it's not exactly R. It's what I meant by that. It's like it's the scaling factor that gets popped out when you're converting to spherical coordinates. Okay. Let's try one. Yes? Let's try one. Because that was too much of me talking. Let's play with one now. So let's see. So let's say it says find the volume of a solid E that lies above. Nope, the volume. I'm doing that one on purpose. To review something. That lies above the cone. Z equals the square root of 3x squared plus 3y squared. And below the sphere x squared plus y squared plus z squared equals 25. If I don't tell you hypervolume, then I have to give you the function to integrate. But if I ask you for volume, then it's needed that you understand you're integrating the function 1. And I was going to review that later. Okay. Is this cone facing upward or downward? The square root is positive, right? So it's going to be, z has to be positive. So let's see. So I try to get a sketch here. I got a cone that's going up. And then I have my sphere like this. So you probably have had a problem like this in your homework. Okay, where it was below the sphere. But remember, what does it mean to be above a cone facing up? It means you're inside the cone. So it's this guy right here. Does that look familiar to one of the homework problems? And you probably didn't like it. Okay? But you're going to see that doing that problem in spherical is going to make the integration a lot easier. Okay? I have to put you through the dirty work first. I would appreciate the spherical coordinates. Okay, so let's say you're on the test, you're like, okay, by the way, I'm not going to tell you what to do on the test. You get to choose either spherical, sometimes cylindrical will work. That's going to be part of the study. And when I do a review, that's part of what we're going to focus on. Okay, so you say, okay, I see a sphere, so that probably means I want to use spherical coordinates. Okay? Because it makes equations of spheres very easy. So this guy's my sphere. How can we write this sphere equation in spherical coordinates? It's just going to be rho squared equals 25, which is just rho equals 5. Bam. Okay, I got my spherical equation. You always use positive for rho, regardless if it's opening upward or downward, because it's distance. Yeah. And then you got your cone. Okay, here we are going to have to do a little bit of algebra. It's going to be similar to what we did earlier. Let me write it like this. It's going to be similar to what we did earlier. The z is going to change into spherical. Rho cosine phi. The 3 stays 3. What was my little tip to you? That's just r squared, right? So then we end up with the square root of 3 times r. Oh, but then you square root it, yep, so you get r. What is r in spherical? Wait, what? What's rho in spherical? Rho sine, which angle? Phi, yeah, careful. If you wrote theta, that would have made it from rho. All right, so it's very similar to what we did already, okay? Divide both sides by rho. So they cancel out. Cosine of phi is root 3 sine here. Divide, this time you guys want to divide by cosine or divide by cosine? Okay. Divide by cosine. So you end up with 1 root 3, what is that, tangent? Tangent of phi. So then what do we get that tangent equals? I'm running out of space. 1 over root 3. So yes, here again you need the inverse form, inverse trig, or the unit circle. Someone help me out here. Let's see, let's use a 30, 60, 90 triangle. 30 is the small angle. Oh, this is not to scale, hold on. 30, 60. 30 is a small angle, 1, 60 is a larger angle, root 3. And then Pythagorean theorem will give you that this is 2. Okay? So, which angle gives you that tangent is 1 over root 3? Tangent is opposite over adjacent. Which one? Opposite over adjacent, right? Opposite over adjacent. 30. So pi over 6. No, fucking trade, right? Trade. Okay. What does that mean, guys? What is that? What information did that tell us? Yeah, it tells you the angle that this cone slanted at in terms of phi. And it tells you that phi rotates, it rotates down here at pi over 6 radians. That's what that told you. Okay? Because now you want to know that information because you need to find your bounds for phi. Right? So if I want to start bounding, I want to find these bounds. Let's start with rho. Let's start with rho. When you guys did polar, remember I was telling you R, you visualize it as like a laser starting from the origin shooting outwards. It's the same thing with rho. Start from the origin and shoot a laser outwards. If I shoot a laser out, it's going to start from here and then shoot out towards, what's the farthest it goes to? It goes up towards 5, right? That's where that was important. You see that? What's the smallest it can get to? 0, right? So you get rho goes from 0 to 5. What about theta? Yeah, that guy's rotating all the way around because it's the sphere. It's rotating all the way around. Is that okay? Okay. So that one's rotating. Now, if I said the first octant, then what would theta be? 0 to pi over 2. It was the first octant. Okay. But it didn't say that, so it can go all the way around. Now, what about phi? That laser, right? That rho laser starts at the positive z-axis. It goes from 0 towards the slant of the cone, pi over 6. That's why you needed that information. That's why we needed all this work here. So it goes from 0 to pi over 6. What if this cone was downward? What would be the bounds for phi? It was a downward cone with the same slant like this one. What would be the smallest value for phi? The laser doesn't touch, if it was here, right? The laser, that little imaginary laser, it's not touching my solid, it's not touching my solid until it gets here. What angle is that? 5 pi over 6 to pi, because remember phi goes as high as pi. So then it would have been 5 pi over 6 to pi. It was the downward cone. No, it's the upward one, so that's going to be around. So then if we put all this together, now back to Charlie's question. Or I think somebody who asked me, or no, I think you asked me. Someone, one of you guys asked me, will you tell us if I have to do hypervolume or volume, right? Because this is volume, when we did properties of triple integrals, we learned that to find the volume of a solid, all I had to do was triple integrate the function 1 over that solid.
if you integrate the function 1, then you do get volume. The hypervolume equals the volume of the solid. That's basically why it happens. Okay? So if it asks you for volume and you're trying to use a triple integral, just make sure you triple integrate the function 1. Okay? So let's see here. So I want to convert this using spherical coordinates. Okay? While at the same time remembering, right now my function f is just 1. So I don't really have to do anything with the x's and the y's and the z's. But this guy pops up. Okay? You switch to spherical. So I still have 1, but now the dv gives me a rho squared sine phi. Or phi, yeah. And then we're going to do rho goes from 0 to 5. Theta goes from 0 to 2 pi. And then your phi is going to go from 0 to pi. And so we're going to do d rho, d theta, d phi. Oh, dang it. Ah, there. And look at that. It's beautiful because these are all scalars. And this is just a product of separate functions. So you can separate it into a product. So this could become like this. What's the function for phi is sine phi, right? So we're going to bring that into its own little world. Sine phi d. What's the function for theta? I guess 1, yep. 0 to 2 pi. And then the function for rho is rho squared. So you just do those 3 easy integrals and then you get your answer. Did I do it for you guys? Oh god, yeah, okay. The answer looks kind of gross, but 125 pi 2 minus root 3 over 3. You work it out. The pi over 6 is what makes it a little bit nastier.
Do we have to convert our answers back into a particular format?
Nope. Nope.
So you don't have to do approximate value?
Say it again?
You don't have to do approximate value?
I would prefer this answer, but if you want to approximate it, that's fine. Yeah. Okay. Sometimes it actually helps to approximate it just to see, like, this answer can't be negative, for example. It has to be positive because it's volume. Well, that's happened. Exactly. Yeah. All right. I'm going to leave with Dylan's question. Dylan's question was, do we have to convert anything back? And the answer is no. And we're going to learn tomorrow, Thursday, why we don't have to. Yeah. And that's it. That's the last section of chapter 15 on Thursday. All right. Pi. We're right at pi time.